Good morning and good evening, everyone. I'm Jinfeng Zhang, a researcher from Rigging AIP. Today, I'm going to host the TrustML Young Scientist seminar. Before that, allow me to briefly introduce Rigging AIP to our valuable guest, Eric. The full name of Rigging AIP is the Rigging Center for Advanced Intelligence Project. AIP was founded in 2016 as a research center for the next AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI fundamental technology and its real-world applications. AIP encourages the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in the near future. Today, we feel very honored to have our guest, Eric. Eric Wong is an incoming assistant professor at the University of Pennsylvania. Currently, he's a postdoc researcher at CSIL at MIT, advised by Alexander Margin. His work focuses on the foundation of reliable data-driven systems, building on the element of machine learning and optimization to diagnose, understand, and develop the system for real-world settings. He's a 2020 Silber Scholar and received an honorable mention for his thesis on the robustness of deep networks to adversarial examples at CMU. Let's welcome Eric to share his research with us. Hi, Eric. You can get started your talk.
All right. Thank you, Zhengfeng, for the introduction.
You're welcome.
All right. Let's see. All right, that look good?
Great.
Okay. Yeah, so let's begin. Yeah, so today I'm going to talk about what I like to call debuggable deep networks. Okay, and maybe just to set this up a little bit, I'll just give you some, this is a trustworthy machine learning sort of series, so maybe these are all sort of familiar sorts of topics, but I guess one of the biggest challenges that I see for machine learning going forward is that oftentimes and then like quite alarmingly, actually frequently, is that the models that we train and the models that we build simply just don't always behave the way that we really want them to. So for example, this is one example that many of you might be familiar with. Some researchers built an AI for diagnosing skin conditions from pictures. And according to their data set and everything, it was as accurate as a professional dermatologist. But then what they had found out afterwards is that actually turned out that this AI that they had built was actually paying attention to whether or not there was a ruler in the picture. And so this AI was actually using the presence of a ruler to determine whether or not your skin tumor was malignant or not. So this is not really something that you'd want to have in the healthcare kind of AI. And now we've seen many of these kinds of examples throughout machine learning history, so not just in healthcare, where models that are highly accurate turn out to be accurate for just the wrong reasons. So in another example, researchers found that if you had an animal detection classifier, it actually relies really heavily on the backgrounds and can't actually generalize to new locations. So in the example that I have here, it actually turned out that if you take like a state-of-the-art algorithm for classifying animals such as cows, it could not identify cows when they were in unfamiliar scenes such as beaches. And just to give you one more example to round this out, researchers had found that if you have an AI system for detecting pneumonia from these X-ray scans, had actually learned to identify exactly what hospital the X-ray was taken in. And so the AI was actually using the location of the X-ray, so the hospital that it was taken in order to decide whether or not you have pneumonia or not. So all of these kinds of examples that I've just sort of shown you is what I would call a bug in the machine learning system. So enough examples. How are we as machine learning researchers supposed to discover these kinds of problems in the first place? In other words, how are we supposed to debug our machine learning models? So let's take some inspiration from what people have done in the past, and actually let's look at software debugging. Because people have been debugging software for a very long time now, and they are in fact quite good at this. And so what you see is that software debugging actually has 5 main principles. So first of all, The first principle is that you've had to first recognize that a bug even exists in the first place. And once you know that the bug exists, then you need to be able to isolate the bug and then identify what's the underlying cause of the bug. And then finally, once you figured out the cause of the bug, then you can develop a kind of fix and then eventually apply the fix and then test if your fix was correct. Okay, so these sort of 5 steps is what are sort of the principles of software debugging. And if you have a system or a scenario that allows you to follow these 5 principles, then in theory, we would have what I would call a debuggable system. So is machine learning debuggable? Can we actually use these principles to debug our machine learning models instead of just the usual software regime? And so today, I'm just going to focus primarily on these 2 middle principles. So isolating the source of the bug and identifying the cause of the bug. So in other words, when we take this over to machine learning systems, how do we isolate or identify the bugs that we have in our models? Okay, and so of course, the bugs can be things like the examples that I showed earlier with the cows on the beaches or the hospitals of the X-rays. So to answer this question, let's go back to a fundamental debugging primitive that if you're a computer scientist, you've probably used this all the time. Because if you look back at the last time that you wrote a computer program, you probably had some kind of bug in your program and you needed to debug it, right? And how did you debug it? Well, one of the most basic tools that we use to isolate and identify bugs is to just comment things out and turn it on and off and see what happens, right? So this is sort of a basic primitive of turning things on and off. So what happens now if we try to apply this primitive of turning things on and off, but to a deep network now, instead of the usual lines of code in software? So let me give you an example. Let's take a image classifier here. So it's trying to classify this duck. And the deep network here turns out to incorrectly classify this as a pigeon. How can we figure out why the deep network made a mistake here? So we could, for example, turn off some of the features in our input and see if the output changes. Alternatively, we could also try turning off some of the neurons in the model and see if the output changes. So I've sort of represented this here by blacking out some of the pixels or blacking out some of the neurons. And if you toggled the parts of your model or the parts of your data, then in theory, this would, according to the debugging principles, allow you to identify the parts of your data and the parts of your models that contributed to this incorrect prediction. And in fact, many existing interpretability tools that exist today for deep learning rely heavily on this primitive to explain what the model is doing. But now, if you try to use this classic debugging primitive, in practice, what you'll find is that there's actually a major problem with this. In particular, when you toggle the parts of your model or some parts of your input, you'll actually find that you can barely learn anything about the model. So specifically, if you try to toggle a few neurons or a few features, regardless of which ones you pick, you'll find that the model's prediction barely changes at all. And in fact, in order to get the network to output anything else, you have to turn off an enormous number of features or neurons. In fact, so many that the resulting prediction that you get is effectively useless. And so why is this the case? Well, it turns out that deep networks are actually highly redundant. And while this redundancy can help models reach very high performance levels, it also makes these models extremely difficult to debug. So consequently, in principle, standard deep learning is actually fundamentally incompatible with the principles of debugging. Because with this amount of redundancy, you simply cannot isolate or identify the bugs that you have in your model. So if the standard deep network is fundamentally not compatible with the principles of debugging, what can we do? Well, instead of trying to come up with an ad hoc kind of explanation or a debugging protocol for standard deep networks, here's a different question. How can we actually redesign our deep networks to naturally have a sort of principled way to explain or debug what's going on in a way that is both accurate and concise? Or in other words, can we make the deep network more debuggable? So in today's talk, I will be discussing a bit about how we can tackle this problem from the redundancy perspective. And so in particular, what we're going to do is I'm going to tell you about how we can redesign the deep network to be compatible with the debugging principles by reducing the redundancy. And this will ultimately let us isolate and identify the bugs that we have in our machine learning models. So let's first take a classic or sort of natural view of the deep network as the following two components. This is a very common take, where we take a deep network and we consider it as a deep feature extractor. So this is the majority of the deep network, followed by a linear layer. And so this lets us decompose the problem of debugging a deep network into two subproblems. First, we have the subproblem of interpreting the deep features created by our feature extractor. And then we have the second subproblem of interpreting this linear aggregation of these deep features by analyzing the final linear layer. And this analysis of the final linear layer is sort of a widely used primitive that is done all the time in the field of statistics. Now, this natural view of a deep network has a substantial challenge, because even though the linear model is conceptually easy to understand and very simple, the final linear layer of a typical deep network is in practice enormous. So for example, a typical ImageNet classifier has about 2,000 deep features, and the final linear layer has about 2 million parameters. So consequently, the sheer scale of deep networks makes analyzing this last linear layer completely infeasible for humans. So how can we make this more viable? Well, one possible strategy here, a very natural strategy, is to just simplify this linear layer with sparsity. So as an example, what we could do is we could focus our attention on a much smaller subset of the deep features, which makes the corresponding analysis much more feasible. So as an example, instead of trying to analyze all of the features in your last layer, a natural idea is to focus our attention on only the most important features, or the top K features, such as the ones that have, for example, the largest weights. Largest weights is sort of a natural way to assign an importance of the features and just say these are the top K, the most important ones. Now, unfortunately, what you find with this approach is that it has several issues. First of all, what you'll find is that the top K features, if you use only the top K features to make a prediction, this is actually much less accurate than the original model, and so it does not fully represent the original model. So for example, in this plot here, which shows the accuracy of an ImageNet classifier, if you drop from using all of the features, so that's the accuracy represented by the blue column, to only the top K features, you drop to the orange bar here, which is about a drop of about 15 or 20%, which is a substantial amount of accuracy. And on the other hand, the second problem here is that the top K features that you use here are extremely redundant and can be easily replaced with other features. And indeed, what you'll see here on the plot is that the remaining features of your ImageNet classifier here, so the rest of the features outside of the top K, are almost as accurate as the top K features. So the rest of the features here are shown in the gray bar. And so consequently, it's not really clear whether these features that you're selecting with the top K are even really important. And so interpreting just the top K features can potentially paint a really misleading picture of what the original model is doing. And so these kinds of issues make it virtually impossible to follow your debugging principles. If your top K features don't represent the original network and they're completely unnecessary, you could use any other features instead, how are you supposed to isolate a bug or even identify why that bug is happening? So what we're going to do now is ask the following. How can we actually redesign the deep network to address this issue? So one general tool that we've developed in the past couple of years to help us make deep networks more debuggable is the simple idea. It's just to use sparse linear layers. And the idea here is simply to sparsify the last layer of this deep network. And now I won't go into too much detail at this point into how this works. If there's time at the end, then I can talk about it a bit. But this simple primitive, what it ends up doing is it actually makes the neurons in this last layer significantly more debuggable. And at the same time, what we're going to do is we're going to leave the rest of this model completely intact. We're not going to touch it. And what this is going to allow us to do is actually keep almost all the accuracy of the original model. And so as it turns out, this idea of using a sparse layer at the end of your deep network actually solves this problem with the redundancy that we saw before and makes the model more compatible with the basic debugging principles. So in contrast to before, which we saw here on the left, the sparse layer now, if you use a sparse layer now, this is now shown on the right, and you look at the top K features, you'll find that the top K features of your sparse layer actually reflects the whole model. So the orange and the blue bars here have almost the same accuracy. And so the sparse, the top K features here actually almost completely encapsulate all of the model's predicted process. And on the other hand, the top K features of your sparse model actually contain very different information from the remaining features. So if you compare like the orange and the gray columns here, the top K models are very predictive, but the rest of the features are not useful at all. And so this solves sort of the problem that we had before when we were trying to interpret the top K features of the dense model. And what I said here was that you don't lose that much accuracy, which you saw before with sort of the orange and the blue columns. But in fact, I can show you, let me show you exactly how much accuracy we can retain with a sparse linear layer. And so here what I have is the accuracy curves for several vision and language classification tasks. So here the y-axis is test accuracy, and the x-axis is sparsity in the last linear layer. So as you go to the left, you get more sparse, and as you go to the right, you get more dense. And the rightmost point is completely dense, and the leftmost point is completely sparse. And now if you look here, what you'll find is that you can actually get linear models that are up to 2 orders of magnitude sparser for just a very small drop in accuracy. So as an example here, you can go from about 2,000 ImageNet features to just about 20 features per class. And this comes at a cost of just about 5% accuracy. And in fact, in some of the language settings here, it actually turns out that sparsity can actually improve your accuracy. So this actually doesn't come at a very big cost. So I've said a lot at this point about debugging principles and about sparsity and about how this doesn't lose us accuracy. And you might be wondering at this point, how does this actually affect debuggability in practice? So, to give you a more concrete example into how all of this sort of plays out, let me just give you an example of how this works in practice. So the setting for this example that I'm going to give you now is about toxic comment classification. So suppose you have a bunch of online comments and you'd like to be able to identify whether a toxic is comment or not as a sort of online content moderation tool. And so for example, in the task here, Perhaps you'd like to classify the following sentence about Ed as a toxic sentence, where here I blacked out certain words that are just a little too vulgar to show on the slide, but you can fill in the blank with your imagination. It's a pretty toxic sentence. And on the other hand, you'd like to be able to classify sentences like this about Barack Obama being the president. This should be classified as a non-toxic sentence. And so this sort of problem setting comes from a Kaggle contest that was held back in 2018. And so what ended up happening is that it turned out that if you trained a standard language model on these toxicity datasets, what you'll find is that the model is actually biased towards certain identities. Specifically, some researchers had found after the competition that the language models had actually learned to associate identity terms as toxic, regardless of whether the sentence itself was toxic. So as an example, let's take this previous sentence about Barack Obama being president. And this was correctly labeled as a non-toxic sentence by the language model. But now if we instead turn this into a sentence about Barack Obama's race, the model incorrectly believes that this is a toxic sentence. And in fact, it doesn't really matter whose name you put in here, because the model just believes that sentences of this form are toxic sentences. So instead of coming across this bias by accident after the competition, how could we have actually discovered ahead of time that the model was actually biased in the first place, potentially using these kinds of debugging paradigms? So let's just use the sparse linear layers that I talked about earlier and use these for the toxic language models. And what happens when we do this? Well, so for these models, let's try to interpret the neuron that most contributes towards a toxic prediction. So in this case, it's the top k, where k equals 1. And here what I've done is I've represented a neuron with a word cloud, where the words in this word cloud are those that most activate the neuron. And now if you look at the word clouds here for the neurons of a standard model, you won't actually see many identity terms. There are a couple, but they're not very prevalent. And in fact, if you count them over all of the neurons, you'll find that the identity terms only make up about 7% of the word clouds over all of the neurons. So if you try to inspect the standard model for biases, it is not entirely obvious that there is an identity bias at all. Because what you're looking for is making up only 7% of the word clouds scattered across all of these neurons. Now, in contrast, let's take a look at the neurons of what I call debuggable layer, or the one that uses sparsity. And then what you'll find is immediately the bias is much more obvious. So if you look here on the slide, the word clouds here are now filled with identity terms. And in fact, if you measure it, about 27% of the word clouds over all of the neurons of your sparse layer now consists of identity terms. So the end result here is that by removing the redundancy, our sparse linear layers, we're actually able to make the biases in the model substantially more visible. So in other words, we were able to sort of identify the bug in the model. Now, just to finish up this example, it turned out that after they discovered that there was this identity bias in the competition, the holders of the competition ended up hosting a follow-up competition for creating a de-biased model. So they had these new metrics that measured how biased their model was, and the new competition was to create a toxic classification model that was de-biased, so one that was not prone to these kinds of biases. And so according to the metrics of this competition, the winning models of this competition were supposedly de-biased. But how do we know if the winners of this competition really succeeded? Well, let's apply the same methodology from before, and again use the sparse linear layers on this newer debiased model and see if we can debug the model. And what happens now is if you inspect the top neurons of the sparse debuggable layer, you get something like this. So here what I'm showing you here is the top 3 neurons for detecting non-toxic sentences. And what you can see here is that rather than being unbiased, there are actually tons of identity terms captured in these neurons. In fact, if you measure this, actually about 43% of the words in all of the word clouds for all of the neurons in the sparse layer are actually identity terms. So what happened here? As it turns out, in order to minimize the metrics in this competition for measuring bias, the model had to explicitly learn to associate identity terms as non-toxic. So consequently, the resulting models that came out of this competition weren't actually debiased. Instead, the bias was actually even worse and just flipped to the opposite class. And so indeed, we were actually able to confirm that the biases that we discovered in these models actually affected its decision process. So to give you an example, let's take this toxic sentence about Ed from before. And this, the model is correctly able to identify as a toxic sentence. But now, if you add an identity term, a biased identity term, such as Christianity to it, the model suddenly now thinks this is no longer a toxic sentence. And this is not just a toy example, because if you do this more systematically, it turns out that if you just add random biased identity terms, such as Christianity, to just random toxic sentences, you can actually flip the model's prediction about 74% of the time. So this is a significant bias in the language model that our sparse linear layers actually helped us identify. And this is something that actually affects the way the model makes its predictions. And on a more general note, okay. All right. Yeah, so on a more general note, this example sort of highlights how the way we think about biases and reliability need to go beyond sort of like these specific metrics, such as the one in the competition, because as we saw here, deep networks can almost always find unexpected ways to satisfy even reasonable criteria. So this makes need to be able to debug these issues even more prevalent. All right. Also, if there are any questions from the audience, feel free to interrupt me at any time. I'll try to leave some time at the end as well if there are any questions. Okay. Okay, so in the toxic language setting that I just talked to you about, it was at least quite obvious to us, us, the researchers sort of looking at this, that the bias that we discovered existed after we used these sparse linear layers. But how do we actually know that the sparse linear layer actually helped us? Right? Did the sparse linear layer actually improve debuggability? This is an important question because as researchers, we are also prone to confirmation biases, and we might actually just be hallucinating the results that we want to see, which begs the following question. How do we actually quantify how debuggable a model is? So what we really care about, right, is whether the methods that we produce can actually help humans understand these models for the purposes of model debugging. And one way to evaluate this is to measure what is called model simulatability. In other words, this is how well can a human simulate the model. And so to measure this, there are several ways in which you can measure this, but what we did here is we designed a study to measure the simulatability of our models. And the study sort of goes something like this. Suppose we have an example input here, and the model is predicting a cow. And so our goal here is to see how well a human can simulate this model when using whatever kind of explanation or sparsity explanation that we give them. So specifically, what we're going to show humans is information from the sparse linear model and the corresponding feature interpretations. And then we're going to ask the humans to see if they can emulate the original model. If the human can guess the same answer as the model, then they have successfully simulated the model. And note that this is regardless of whether the model is correct or incorrect, right? The goal of the human here is to just predict what the model would predict and hence simulate the model. But the design of this kind of experiment is something that actually takes a bit of care to do correctly. So as an initial attempt here, consider a simple setup where here we can consider showing the humans the set of sparse features used by the model to classify a cow. And this is what I would call like the explanation of the model that we're going to give the humans. So we say this is how a model classifies cows. And what we can then do is we can show the human a candidate object for classification. And then we can ask the human, do they think the model is going to predict a cow or not a cow? Unfortunately, if you run the experiment in this way, it is subject to confirmation bias. So specifically, humans have a preconceived notion of what a cow should look like and may base their answer on whether the image itself has a cow in it. So for example, suppose the model has it where we ask we are giving as a candidate object a different cow, for example, the cow on the beach, and the model is unable to detect the cow on the beach, so it predicts something else, like a crab or water. If we asked a human, what would the model predict? A human might actually simply predict cow simply because they see a cow, regardless of what the explanation actually shows. Right, so this is a problem. And so you have to actually carefully measure this simulation in a study without this kind of confirmation bias. And so the way in which we do this here is that you actually have to hide all the information about class labels. Otherwise, it turns out that humans just predict what they see. And yeah, if you tell them that this is explanation for a cow, they will hallucinate cows in everything. And so what we need to do is we need to force humans to only make predictions based off of the explanation instead of their own biases. And so the way we do this is by first showing features, but now for a hidden class. So it's important that you don't tell the human what the class is being predicted here. And what you do show is you show multiple candidate objects now. Because the problem before is that we showed them one object and they would just base their prediction off of the one object. And so now what we do is the goal here is now to ask the human to pick the object that best matches what the model is looking for, or what the hidden class is. And this way, this forces the humans to base their simulation of the model off of the explanation that you gave them. And they have to select from these multiple candidate objects. And this turns out to almost completely eliminate the confirmation bias that I described on the previous slide. And once you do that, it actually turns out that once you've measured the simulatability of these models, it turns out that humans are about, in this study that we did, humans are about 30% more accurate when you ask them to simulate the model that was with an explanation with a sparse layer, as opposed to the dense layers. And so this sort of study suggests that sparsity does, in fact, improve the debuggability of your deep network. Okay. So let me see. So, okay, now let me give you one other way in which we can measure the debuggability of a model. And this is via their model, the model's misclassifications. So consider the problem of understanding why a deep network made a mistake. So consider the following web page. and suppose that it's been misclassified as a menu. And what it turns out is that many of the misclassifications that deep networks make can actually be largely attributed to just a few problematic features in your final linear layer. So for example, this is a visualization of the feature in the linear layer that is the key contributor to this misclassification. And in fact, what it turns out is that if you turn off these problematic features, you can actually fix the prediction in many cases. So this problematic feature is a very reasonable explanation for why the model made the mistake, because simply by turning it off or by toggling it, you can correct the problem. But how can we evaluate this more rigorously and actually measure this and verify that these problematic features are actually present in this misclassified input? So in order to evaluate this, we designed a misclassification study. So as opposed to the simulation study, we're now going to study misclassifications. And so the way this works is we're going to show a human an image that was misclassified by the deep network. We are then going to show a human the feature from the predicted but incorrect class, as well as a feature from the actual correct class. And then we are going to ask the human which feature best matches the shown object. So if the human selects the feature of the incorrect class, then this feature actually explains, at least according to the human, why the model predicted the incorrect class. And this is in a way that is now actually recognizable to humans. And so if you do this in this study, we actually found that for sparse layers, or for the sparse models, humans are actually able to identify the top feature of the misclassified class as a better match than the top feature of the actual true class more than 70% of the time. And so this suggests that these features, that these top features of the misclassified class actually explain in a human recognizable way something in the image, in the misclassified image, that contributed to the incorrect prediction. Okay. So those were a couple of ways in which we could measure exactly how debuggable, or whether or not our model is actually being debuggable or not. And so I think in the last bit of this talk, I will just briefly, so I skipped this in the beginning of the talk, but I'll now give a little bit of the details on what's going on behind the scenes here, because sort of this whole time I've been talking about, debuggability, sparsity, accuracy, and then some of these human studies. But at the end of the day, the core primitive here is to replace your dense linear layer with a sparse linear layer. And as it turns out, when you try to do this for modern deep learning settings, you have to do this at scale. And if you try to use sort of the classic sparse linear layer solvers, they don't work at scale. So let's dive into this in a little bit more detail. So just recall here that the solution that we wanted to do here is to explicitly refit this final linear layer to be sparse by construction. And so what we're going to do is we're going to use what is the classic problem from statistics. It's called the elastic net. So this is a well-known problem for fitting sparse linear models here, written on the center of the slide. All right, so it's just a linear regression problem with some regularization terms. So just to unpack this a little bit, in the term on the left here, we are fitting a linear model on the deep features of our pre-trained deep network, while on the right-hand side here is the elastic net regularization term, which encourages a sparse solution. So in particular, the L1 term makes the solution sparse, while the L2 term makes the solution unique and gives it nice properties. So this is a, this is a problem with several appealing properties. It's a convex problem, it has a unique solution, and there are some very well-known fast solvers from the statistics literature. But as I alluded to previously, as it turns out, if you try to take one of these classical statistics solvers, they just don't scale to ImageNet size datasets. So one of the things that we had to do here was actually make our own solver that does. Okay, so for the next few slides, I'll just go into a bit of detail into how you can actually scale the elastic net to ImageNet size datasets. So this is a bit of a, so there'll be a bit of detail here. So to begin, let's actually just take a look at a classic approach from statistics for solving the elastic net. This is called the a path algorithm. So specifically for a range of hyperparameters alpha k through alpha 1, we're instead going to solve a sequence of elastic net problems where this regularization term of alpha has decreasing regularization. So in the equation here, this is the same elastic net problem, but the regularization term is weighted with alpha. And so typically what you do is you start with alpha 1 to be large so that the solution is completely sparse, and then you gradually decrease it until the solution is completely dense. And so why do we do this? Well, at a first glance, this seems more expensive, but actually, it seems more expensive because you're solving now multiple elastic net problems instead of just one. But it turns out that as you decrease the weight of alpha, you can initialize the starting point of your optimization problem with the solution of the previous alpha. And so this is a common trick in optimization known as warm starting, and it makes solving each preceding alpha, each optimization problem for each alpha I extremely fast. And this also has a additional benefit where instead of having a single sparse solution corresponding to a single sparsity regularization value, you actually get an entire range of is there something in the chat? I see. Okay, I think I passed by some of these. I guess I'll get back to these questions in the end. Okay, so yeah, so actually you get a range of sparse solutions from completely sparse to completely dense. And so this sounds great. And you can actually solve this now for a wide range of sparsity levels and choose your optimal sort of hyperparameter here. So you can choose any amount of sparsity that gets whatever accuracy sparsity trade-off that you want to have. But we still, at the end of the day, need to solve the actual elastic net optimization problem at each one of these alphas. And in order to do this, previous work in statistics have created this blazingly fast coordinate descent solver. And to this day, this is considered sort of the gold standard in solving the elastic net, but it just simply wasn't developed for big data settings. And in particular, since it's based on what is known as a coordinate descent solver, it's just struggles to solve problems with even more than a couple thousand examples, let alone ImageNet. And so just to give you a brief highlight of how we can actually solve the elastic net at scale, let's take a look at sort of a classic workhorse of typical deep learning, stochastic gradient descent. This works really well for deep learning settings since it's sort of scalable, it converges relatively quickly. But as it turns out, stochastic gradient descent on its own is actually too slow and inaccurate for solving this elastic net problem. So in particular, although the SGD algorithm can get close to the optimal solution, one of the properties that it's well known for is that it actually struggles to actually converge to an optimal value. So it sort of oscillates here as shown in the figure on the right. And in particular, it's known to have sort of an order of magnitude slower convergence than gradient descent. And you have to carefully schedule the step size. And for the elastic net in particular, this oscillation often means that you have actually oscillating sparsity patterns where the sparsity solution will often flip between 0 and non-zero. And so this is not good. So sort of the key solution here to save the day, what we actually ended up doing is use sort of these more recent developments in the optimization literature. In particular, it's a class of methods known as variance reduced gradient methods. And these kinds of methods can effectively solve all the problems that I mentioned on the previous slide. And to give you sort of a high level intuition as to how this works, basically what happens is that in stochastic gradient descent, typically what you do is you estimate the gradient with an average gradient over a random mini batch, but this has very high variance. And this high variance causes sort of all the problems that I just discussed. So what the variance reduced gradient methods, as sort of the name kind of suggests, is to reduce the variance of this estimate and make it more stable. And one such method, for example, here is known as the saga method. And sort of just by using some tricks and storing some old gradients in a table, you can actually get a much lower variance estimates for your gradients. And what this ends up doing is, so let me just step back a bit out of these details and just give you a recap. The solver that we built is effectively a combination of the two lines of work on statistics and optimization. It's this path algorithm that I discussed earlier, where you solve a sequence of optimization problems, but each optimization problem is now going to be solved with a mini batch saga solver. And okay, so that was a bit of a lot, but if you didn't get any of that, so sort of the most important thing here is that if you put these two things together, you get an extremely fast and scalable ElasticNet solver, one that can easily solve an ImageNet problem on a single GPU within a few hours. Something that none of the other ones can do. Okay, so sort of let me take one more step back now and sort of remind us why we wanted to solve these sparse linear models at scale. So what we did here, right, is we wanted to use the representational power of this deep network with an interpretable sparse linear layer and refit that last linear layer to be inherently sparse. And the reason why we wanted to do this was to get a debuggable deep network. Right. And at the end of the day, the sort of the pipeline of this framework is to sort of use feature interpretation tools at this sparse layer and then interpret the results of your ElasticNet solver. So this is sort of like the high level idea of all the sort of the topics that I just discussed. So there isn't enough time for me to go into all of the things that we could do with this framework. So just at the very end here, I'll just sort of briefly highlight a few other things that I didn't talk about today that we were able to show that sort of these sparse linear layers can help you do. So one of the things that that these sparse linear layers can do is actually you can systematically identify the correlations that your model is learning from the data. And the way this sort of works at a high level is you analyze the weights of your sparse layer. And because it's sparse, there are only actually a few overlaps between classes. And these overlapping weights between classes then allow you to pinpoint these kinds of correlations. Another thing that these debuggable networks with the sparse layers let you do is that you can actually discover these kinds of input modifications here that actually change what your model is predicting. So in this case, we can, for example, discover that one of the correlations here is with water and snorkels, right? Because snorkels tend to appear in water. And so if you take these other images, for example, this mask or this sunglasses image, and you add a water background, then you can cause the model to predict a snorkel instead. And yes, and of course, as I mentioned before, you can humans are better at simulating these models. So now just to briefly recap what we have, what I talked about today. So at the very beginning, I talked a bit about how we can reduce the redundancy of these deep networks with sparsity, and this allows us to enable actual principled debugging for deep networks. I also talked a bit about how you actually measure what debuggability is in the first place. And finally, at the very end there, I gave a bit more of the details in how, how we can solve sort of sparse linear systems at scale and sort of these little optimization things that we had to learn along the way. And just as a one final note, we also have some other work on debugging. It's about missingness bias in model debugging. And this is also another line of work, not about sparse linear models, but actually about debugging the debugging tools. So if you're curious about that, you can check that out as well. So I think I think I'll end it here so that there's some time for me time for questions as well as answer some of the questions that were in the chat. Does that sound good?
Yeah, great. There are some questions in the chat box.
Okay, so let's see. On page 23, it seems to require to toggle both the linear model and the inputs at the same time to debug. Okay, I'm not too sure what the question here is. Chao Kai, if you want to unmute and just ask it, then that's also fine too.
Yes, Eric, thank you for your talk today. My question was that in the beginning part of your talk, you mostly mentioned on toggling neuron cells. However, when it comes to page 23, it seems it is also important that how you choose the inputs to check your debuggability. So is this right? I see. So for the neural networks, we can have a systematic way to toggle things like you mentioned in the principles of neural networks by mapping the technologies developed in software. But in the selection of inputs, is there any systematic ways? Because in the later part, you mentioned several clever ways to observe things you want to explain by choosing different inputs, right?
Yeah. Yeah, no, that's a good question. Yeah, so how do you choose what inputs to toggle is sort of the core question that I think you're asking. And
yes.
Yeah, is there a systematic way to do it? I to some extent there isn't, because to some extent sort of what you need to toggle here is going to depend on what task you're solving in the first place. But also to some extent you kind of can. So let me maybe codify this in an example. So for example, in the language setting, it's sort of easy to toggle words, because you can toggle words and you can almost toggle words based on their sort of these importance values. But in sort of like the vision settings, like in the example that I gave, I think over here. So like here, when we in this example on the right, when we like replace the background with water, like you can also imagine just like toggling the background as well, right? And this kind of thing, this kind of pattern here with the water background here is something that you could do systematically based off of the stuff that you learned from the sparse linear model.
I see.
Which is why I would say, like, to some extent you can do it, but at the end of the day, the exact way in which you toggle something is going to depend on the problem that you're actually solving.
I see. So, so I think for this debugging, for the entire debugging problem, it is for me relatively easy that we can have a systematic way for models. But for the entire debugging problem, there is involved another issue of choosing the input, which is not very clear, or there hasn't been a systematic way to do so.
Right, right. Like, so
I
if you
see,
look
I
at
see.
some of the interpretability tools that people use right now, one of them is,
Mhm.
for example, Lime, and the way they do it is they just randomly toggle things.
I see, I see. Thank you so much. Thank you for answering the question.
Yeah, like if we had a systematic way to sort of be able to know which are the things that we're supposed to toggle and then focus our efforts on those in those places instead, I think that would be great. That would be amazing if the way in which we could do this was actually effective.
I see, I see. Thank you.
Let's see, next question here. When we deal with human tests, are there any principles for rigorous results? I see, yes. So with the human tests, so with the examples that I sort of gave in the simulation study and the misclassification study, the biggest problems that we ran into there was to eliminate all forms of human bias. Because if we didn't do any of that, so the main thing there was confirmation bias, right? And when we initially ran the study, we didn't account for this, and the results of the study were completely useless, because basically everybody just all the random people we asked to classify things just classified based on what they saw and not what they thought the model would do. In terms of, I think it would be nice to come up with a set of core principles, but I think sort of the big one that I would say at this point is really to eliminate human biases, especially if you're trying to measure a property of your model. And these human biases can sort of creep in all sorts of ways that you don't normally expect.
I see, I see. Okay. Yeah, okay. Any tricks for doing that, for eliminating the human bias?
Any tricks for what? Sorry?
For eliminating the human bias.
Yeah, okay. So for eliminating the human bias,
Yeah.
You have to, let's see. So I mean, the two things that we had here were to eliminate all of the class information
Okay.
from the question that we asked them, right? Because as soon as you give a human any kind of specific object that they like, a specific class, then they just start hallucinating the class in everything that they see.
Okay.
Whether or not it's actually there or not. So you have to. So when you design the experiment, any question that you ask, you have to give multiple. If you have to show them a picture, you have to show them multiple pictures. Otherwise, they will just see the one picture and then they'll infer that class from the class of the picture. So that's why we had to do multiple pictures, and then we had to also say that we could not say anything about what the model was trying to predict in the first place, because if they know what the model's trying to predict, they just say that that's what the model's going to predict.
I see, yes. That's not easy. Yeah. Thanks for answering my question. Yeah.
Let's see. So Anand has a question here. Does the loss function of the elastic net solver have any impact on the biases that are detected by the model and its debuggability? Okay, yeah, so the loss function of the elastic net solver, right? It's a regression problem with the regularization. So sort of the main factor here is the regularization. And I guess maybe what you might be getting at here is that I did use the elastic net regularization, which is a combination of L1 and L2. You could potentially get sparsity with just L1. So the reason why we ended up using L2 is because it A has the better convergence properties, and it B has the property that if you have very highly correlated features, they will be of about the same weights and they will enter the path at the same time. So this might have actually an impact on the things that are detected, because then you'll have groups of similar features and patterns joining the path at the same time. Does this answer your question?
Yeah, so I just wanted to make sure if I understand correctly that you make the the final dense layer sparse after the model is trained, right?
Yes. Yes.
Okay. Okay. So I mean, so the main loss function is basically somewhat, let us say, your mean square error between what the trained model actually predicts and what you want your sparse linear model to predict.
Oh, I see what you're saying here. Actually, so what we did here is not exactly that.
Okay.
It's instead of trying to fit what the model was predicting, we were actually just trying to fit the original class labels.
Okay. Okay. Got it. Got it.
I see your point though, right? Because it's what you're saying, what you're describing here is having a sparse model that directly is trying to capture the original model, as opposed to what I just described is trying to classify the same problem as the original model.
Yes, exactly. So like, I'm also wondering if these, the loss function that you introduce now and the regularization terms pose any further inductive biases to the final model. So the original model was trained towards certain objective, and you are trying to retrain the last layers and replace it with a new set of weights with based on another objective. So does this change the inductive bias of the model? So how the earlier layers interact with the final layer?
Yeah, so I think you're completely right here in that it does change the inductive bias here. I think the reason why I would say this is because of these earlier. So the earlier slide that I had, let me see if I can get there here. So the reason why I would say that it definitely changes is because of this slide, right? Because if you go from the dense to the sparse one, then the information that it's using here from the different sets of features are almost completely different just based on the accuracy that you can get out of it. As for a more precise characterization of what the inductive bias is, I'm not completely sure.
Okay, okay. Thank you.
Let's see, Yansu has a question here. Can you give us an example of feature interpretation tool that is it more helpful than gradient-based explainable AI? Okay, so the feature interpretation tools that I used here in this talk were primarily feature visualization. So in this case, so for vision, this is sort of the where you do gradient descent in the feature space just to activate a neuron. And then for language, it was with the word clouds. So those were sort of the interpretation tools that I used here. I think the other methods that you sort of put in the chat about gradient-based methods like integrating gradients and these other things, I think these depend on an example. So these are sort of an example-based explanation, as opposed to in this case, we're sort of looking at sort of a more global kind of interpretation, which is why we use this. But you know, the other ones could also potentially help if you did that on sort of exemplar images, actually. So if you took an exemplar image, one that like most activates a neuron, and then ran integrated gradients on it, that could actually be very helpful as well. And then I hope that if that didn't answer your question, feel free to unmute and okay, and then I think there's one last question here, also from Anand. So our prune model about prune models. Okay. Okay, so my suspicion here. So I've not tried this on a completely pruned model, because I know I do know, I'm familiar that like in the pruning literature, you can also you can do the whole network and get it really sparse. So my suspicion here is that the pruned model in principle should be better for debugging. I think the big question is really, is it pruned enough to actually be useful in the debugging, right? So because I know that like the pruning can get like 2 orders of magnitude without losing any accuracy, but 2 orders of magnitude for a model with like 100,000 or 1,000,000 units is still a lot to debug.
Okay, yeah, that makes sense.
What I could imagine is if you had a model that was sort of subdivided into modules and then pruned at sort of the module level, that could feasibly be, I think, more human usable in terms of debugging.
Okay, yeah. Actually, like now, so if sparsity is crucial for the last linear layer, and we have a certain this kind adaptive and dynamic convolutional kernels like being proposed all the time. So could they be used because they kind of provide like, I mean, not sparsity, but they still have like fewer weights compared to like a full-fledged linear layer. So that kind of model design, I don't know if that could be an interesting way to explore debuggability.
Yeah, I think that definitely could. I mean, the main thing here was just sort of to reduce the amount of things you have to look at, right? And if you can do this via some other mechanism, then I think the main question is now, how much do you lose much accuracy? And if you do, how much do you lose, right?
Yeah.
Because at the end of the day, many of the people that I talk to will always ask me, this debuggability is great, but like, I don't want to lose my performance. And at the very least, for the last linear layer, like you basically don't lose anything.
Yeah. Okay. That makes sense. Thank you very much.
Yeah.
All right. Thanks again for Eric's great talk. If there are no other questions coming up, this is the end of today's talk. Thank you again for your great talk.
All right. Thank you, everybody.
Bye. Yeah. Thank you. Bye-bye.